for a moment. So we looked at centering. Let me flip back over here, get this going. Will not work if it's not plugged in. There we go. So we looked at centering here and here. We're going to look at creation of carbide inserts. So our cutting tools. So several different styles of cutting tools, but all of them, not all of them, most of them are coming from carbide. Carbide is a powdered metal, so all of these are just different styles of inserts that we have had, or can use. Okay, some of them are ceramics, but most of them are carbide inserts as that goes around. So carbide inserts are great because they're harder than the material that we're cutting with. And so how long do you think it takes to make a carbide insert? So a carbide insert comes in a pack of 10. I don't think I have any in here. I took some out this morning. They usually generally come in a pack of 10. And then they sell from anywhere from about 20 to 50 bucks a piece. How much you think, or how long you think it takes to make one of those?
8 minutes.
8 minutes, okay.
Per pack, 50 bucks.
Per insert.
Per insert.
Oh, per insert for 50 bucks. And then how long do you think it takes to make one of those? Hour. Okay.
Hopefully not.
I think it's way quicker than that.
Well, we did quick,
I'm gonna say about 25 minutes.
25 minutes.
30 seconds. I'm changing
How much?
45 seconds.
30 seconds. That's when I thought about it, that's what I thought. I was like, oh, I bet they're spitting these things out like freaking rockets, man.
It's probably got cooking.
They do. Yeah. So it's a powdered material.
An hour.
Going back to an hour. Okay.
I'm gonna say 3 hours.
Going 3 hours. So 8 minutes went to 3 hours. You stay at 25?
Probably less than.
You staying at 1.21 milliseconds, whatever. Yeah. Okay. All right. Let's see what it is. So this is just a video. I think it's from Sandvik.
Almost everything made of metal is machined with an insert.
I'm gonna turn.
The insert has to withstand extreme heat and force, so it's made of some of the hardest material in the world. A typical insert is made of 80% tungsten carbide and a metal matrix that binds the hard carbide grains together, where cobalt is the most common. It takes more than 2 days to produce an insert, so it's a complicated process. In the material warehouse, row after row of raw material are stacked. The tungsten carbide we use is either recycled or comes from our own mine in Austria. Cobalt, titanium, and all other ingredients come from carefully selected suppliers, each batch meticulously tested in the lab. Some recipes contain very small amounts of selected ingredients that are added by hand. The main ingredients are then automatically dispensed at different stops along the weigh line. In the milling room, the ingredients are milled to the required particle size, together with ethanol, water, and an organic binder. This process takes from 8 to 55 hours, depending on the recipe. The slurry is pumped into a spray dryer, where hot nitrogen gas is sprayed to evaporate the ethanol and water mixture. When the powder is dry, it consists of spherical granules of identical sizes. A sample is sent to the lab for quality check. Barrels of 100 kilograms of ready-to-press powder arrive at the pressing machine. Up up to 12 tons of pressure are applied, depending on the type of insert. The binder added in the milling room is what holds the powder together after pressing. The process is completely automated. Each insert is weighed, and at certain intervals controlled visually by the operator. The pressed inserts are very fragile and need to be hardened in a sintering oven. The process takes about 13 hours at a temperature of approximately 1,500 degrees Celsius. The inserts are sintered into an extremely hard cemented carbide product, almost as hard as diamond. The organic binder is incinerated and the insert shrinks to approximately half its original size. The excess heat is recycled and used to heat the premises in winter and cool them down during summer. The inserts are ground one by one in different types of grinding machines to achieve the exact size, geometry, and tolerances. As the cemented carbide insert is so hard, a disc with 150 million small industrial diamonds is used to grind it. The excess carbide is recycled, as well as the oil that is used as cutting fluid. The majority of inserts are coated, either through chemical vapor deposition, CVD, or physical vapor deposition, PVD. Here we see a PVD process. The inserts are placed in fixtures. And put into the oven. The thin layer of coating makes the insert both harder and tougher. This is also where the insert gets its specific color. Although the insert has been inspected at the lab regularly during the whole process, it's manually examined again before it's laser marked and packed. After labeling, the grey boxes are ready to be sent out to manufacturers around the world. When the inserts are worn out, they are returned to Sandvik Coromant for recycling. And the process of making a new insert begins.
It's not the same process for cubic form nitride cutters.
I would say so. Okay, yeah, so I would say, we grab that light, please. I would say your CBNs, your ceramics, your carbides are all probably kind of falling within a same process for all of those insert creation. A lot of inspection goes into it. Your inserts, honestly, I think have a large tolerance on them when you look at, when we won't look at insert tolerancing in this class, but when you look at the tolerance of an insert, as far as height goes, when you consider that thing to be a repeatable, replaceable thing in there, where you really shouldn't have to make any kind of offset change. Insert goes bad, you take the insert out, you put the insert back in, you should be able to go straight into the cut. They have about 5 to 8 thousandths tolerance on thickness, and when you're talking about something that's beveled, it changes how big it is, you know. There are some other things that hold it just a little bit tighter, and Scribe Circle would hold it a little bit tighter, but I'm a little surprised by that. So again, what they're doing is they're taking something that's that it's that powdered metal, pressing it together, heating it, and creating that super hard carbide insert. So it's pretty amazing that what you're cutting steel and aluminum was a powder just maybe days ago. Carbide has an extreme temptation with it. So really nothing to do about the class, it's just life in general. Carbide sells for about $13 to $15 a pound recycle rate. And so there's always a temptation, since there's just piles and piles of it around the shop, to start taking it home.
Pretty heavy too.
It's super heavy. It's insanely heavy. Does not take, so I sent a box out, probably 3 or 4 years ago now, about the size of that cardboard box right there. And it was about 60 pounds, to fit into that box. And so I sent like 5 of them out, and at that time Carbide was $20 a pound. And so that was just Carbide that I gathered around the shop, loose Carbide inserts. I would just go around and find them in different places, and I just kept accumulating them. And once I had a couple of boxes, I was like, okay. And so I'm super cheap. So with UPS, they had the box, if it fits, it ships. And so the box was whatever you could fit in the box, they would ship it. And it actually says in really small print up to 60 pounds. And so I packed every one of those boxes with like 55 pounds of Carbide. And so I took it into the post office, and I used all my might to pretend as though they were not heavy. So I'm just laying them down. My freaking arms are probably shaking like crazy. I'm like, hey, I got some boxes to ship. Just made no big deal about it. And they're like, okay, cool, blah, blah, blah. And like the girl goes to grab it, and she's like, he just hit the ground. I was like, that was worth it. So anyways, it's like $1,500 worth of scrap that I got for that. And we just bought stuff with it here. But so I tell that story every year to students. And so I had a student last year call me up, and I was on my way to Kansas City, and he said, hey, you got a second? I said, yeah. And he says, I need 2 things to talk to you about. One's about a new potential job. The other one is just a story that you always told in class. I was like, okay. So we talked about the job. The next thing he goes, remember how you always told that Carbide story about don't steal Carbide from your employer? I said, yeah. He's like, so the shop that I work at, a guy who had worked there for 40 years had been taking a handful of Carbide every day home in his lunchbox, and went to the recyclers. There's only so many places that recycle Carbide. He's like, so he got flagged, and they figured out who it was. Guy's like 5 years from retirement, kicked him out the door. And he probably made a couple $1,000s over the years, of doing it, a handful at a time is, I don't know how much that makes up the difference, but it's also happened over here at Garner, Denver. They have 55-gallon drums full of used Carbide inserts, and guys would just on their way out grab a handful of them and take them, and everything's on camera, so they just caught the guys doing it and just fired them all.
So is there a difference between inserts and a Carbide end mill? I mean,
value-wise, or
sure.
Like how they're made and stuff.
not really. So same thing, powdered metal. I mean, even if you look at a Carbide end mill when it breaks, you can see it's different from steel. It's like granular. Yeah, exactly. It's grainy on the end of it. So your Carbide end mill is built the exact same way. It's formed the exact same way. It's powdered, made into that shape. It's probably a blank, and then they grind the flutes into it. And but it's a pretty amazing process.
I'm after the end mill, not the insert.
Got you going for the big ones.
Yeah.
Good. Yeah. Now I think in my Carbide recycling event, I think I had some like 2-inch Carbide end mills that just came from who knows where. We get weird stuff here sometimes. Somebody's like, hey, I got this 9-inch Carbide end mill that was my cousin's uncle's sister's friend. Can you use it? And it's like beat to death on the end. I'm like, no. What would I put it in? Yeah, I mean, it's this big around. Like, yeah, there's no shank that holds that.
Should've been like, yeah,
Scrap it out. Usually, if something like that comes to me, I'm like, here's what I'm gonna do. I'm gonna take it from you. I'm gonna scrap it, and then we're gonna buy pizza. And they're like, go for it. Usually they're pretty cool. People are pretty cool about giving us stuff. So that's usually that's pretty great. And I always just tell them whenever I take stuff, I'm like, I'm not using this. I'm probably just gonna sell this on eBay. And they're like, that's cool. I just don't want it anymore. All right, sounds good. So as long I'm on the up and up, they know what's going on, so I don't have a problem with it. So, all right, so that's just a little bit about. So just when we're talking about material identification, carbide is denser, heavier. It's just you'll notice the feel when you grab onto a carbide end mill versus a standard end mill. I'll go grab one. I'll go grab a couple just so you can feel the difference, know the difference. Won't be an exact apples to apples comparison, but it's pretty close. So carbide versus high speed. Carbide versus high speed. So roughly the same size. There is definitely a density difference in there. Oh, there's one's already out. The carbide has a lot more density. That's why it lasts so long. That's why it cuts so good. The one thing about carbide is it'll never hold it, or it'll never sharpen an edge. The edge will never sharpen like high-speed steel will. So you can get super sharp, but if you are looking for something that is insanely strong to shear, it's almost always going to be high-speed. So if you're cutting something fibrous or something that you really need a good shear on, you're going to need to use a high-speed steel cutting tool for it anyways.
So on like a carbide drill, like the through peeling or whatever, you know how like they'll have like a high-speed drill, it'll be like straight across pretty much, like your cutting point, but like a carbide will be like notched back a little bit. Why is that?
So oftentimes, I'm not sure if I have one that's close, maybe here. On the carbide drills, that one doesn't really have one on it. So it's really just thinning the edge of it. It allows that carbide drill. So a normal high-speed steel drill doesn't have the density, so it often is going to need center drilling or spot drilling operation before it. So what they do on a carbide drill, 2 or 3 flute drill, they're going to thin the web there. So what they're trying to do is create a smaller, sharper point, so they kind of overlap the flutes on it, so that you don't have to use a center drill or a spot drill with it. Most of the time, if your surface is flat, and you're using anything other than a 2-flute high-speed steel drill, you should not have to pre-drill it or center drill it. Oftentimes we're just center drilling it because we want the chamfer there at the end. So we're going to spot drill it. But if you got a carbide drill and you don't require some type of spot drilling or some type of chamfer that goes on there, you should be able to run the drill straight through. So and carbide's one of those ones that it would prefer to be in cut all the time. So you actually get a better cut, or you'll get longer tool life with the carbide by not heck drilling through it, but just jamming that baby through there. Because what happens with tech drilling is hot, cold, hot, cold, hot, cold, hot, cold, and then you get microfractures on there and it explodes.
It's the same like an insert drill too.
Same with an insert drill. It would prefer to be in the cut the entire time. So that's why on turning, an insert will last oftentimes longer, and when you're talking about physical in-cut time, because it's continuously in the cut, where an end mill, insertable face mill, shell mill, something like that, it seems to last longer, one, because there's 3 to 5 inserts or however many inserts that you have, but they're also not necessarily in the cut as often. So like inserts for a mill, you know, you run it, you face mill it, it goes back in the carousel. An insert's only rated for 15 minutes of in-cut time. So a full-on engaged cut time, 15 minutes, the insert should be shot. If it's not, you're not pushing it hard enough. If it fails before that, you're pushing it too hard. So that's a great way to rate those things. The shop I came from, we used to always try to be insert conscious. Always try to save dollars there. And what we found is that was the worst place. That was the worst place to try and save money. It was kind of like, instead of buying trash bags every day, I would pay you $25 an hour, whatever you make in the shop, to just go carry handfuls of trash to the trash can. Well, it's way cheaper just buy trash bags, right, and throw them in there and do one trip. And so what we were doing is we were really spending hours going over things that were pennies while we were not paying attention to the things that were dollars. And it actually took our Sandvik insert guy to tell us that. He's like, you know, the insert is the cheapest part of the whole process. I was like, no way. And so I go and make a little spreadsheet, do it. I'm like, dude, it's 100% right, you know. So I never told him that though, because I'm way too prideful. But so anyways, that's just some extra for you to know.
Hey, Dustin,
Yes.
back to talking about center drilling or spot drilling.
Yeah.
Would you, so if you've got a drill with a 90-degree point, is it totally pointless to spot drill regardless?
Get it. Is it?
So would you still want to spot drill, basically?
The only reason that I want a spot drill is if my surface is uneven on the top, casting, or I need a chamfer.
Right. So a 90-degree point doesn't make a difference at all.
90-degree point versus 118, 135 really isn't gonna matter. So if I've got a 90-degree drill, it's not gonna leave me any kind of chamfer because it's gonna blast the hole through it, you know. If I need some kind of chamfer and I've gotta do high production holes, I would have the chamfer built onto the tail end of that drill. I'd custom buy a drill that had, and you can buy the ones that had that bolt-on chamfer on the backside. Those things never last a long time. They'll do 300 or 400 holes and then they just like disintegrate. So, but yeah, you can buy a drill that already has the chamfer on it. Yeah, steps up. So it goes like this. So here's your drill point. And that way, there's the body of it. Then that way, when it goes in to do the hole, you get chamfer on there. So you can do that. That's a good way to save yourself some time and money and tool changes. And especially if you're running a machine that, so like, if you got like a tool room mill from Haas, they don't have tool changers on them. So you're trying to conserve as many operations as possible. So if you can, like they make a drill reamer, that's the same way. It reams on the backside of the drill, so you drill it and then it goes into reaming. You know, those are ways to save some operations, save some tool changes. So, okay. So let's talk plastic versus elastic deformation. We'll talk strength, ductility, and toughness. We'll do body-centered, cubic-centered crane structures. So this is what's inside the material, how it moves. Every piece of material, like we've got some characteristics or some parameters on our material, we oftentimes want it to bend and move and shift. So think about it like this, even a roll cage on a race car, you don't want it to be ultra rigid, do you? You want it to flex, right? If it's ultra rigid, as soon as it has impact, it's got the opportunity to crack. So you want it to bend some, you just don't want it to bend so much like a Twizzler, right? So where you're just like, oh, now I'm wrapped up inside of this thing. So you want some flex in there. So kind of about trying to find that balance of what you want. So we're gonna look at today, hopefully we'll be able to break some stuff apart. I've got some little pieces that are, they're 3D printed, and they're 3D printed in different ways. So they all look the same, but they're 3D printed different ways. And how we printing is a great way to figure out what's strong versus what's not. Because printing, have you 3D printed before? Anybody? Okay, yeah. So inside your 3D printer, it gives you the options of, you want this thing to be solid inside, you want it to be hollow inside, you want it to be a honeycomb inside, diamonds, triangles, whatever it might happen to be. So we printed a couple of different kinds, using anything from just regular nylon to Kevlar, fiberglass, a couple of other things. We'll just see what happens when we put some pressure against some stuff. All right, so we'll look at plastic versus elastic deformation first.
Do you know the best place in your house to potentially save money? Not the garage, not the kitchen, but here, the roof.
When we hear the word elasticity, the first picture that comes to our mind is something like this. But is this really what elastic means? We will find that out in this video. Let's take an example of a helical spring. When a force of compression or tension is applied, the helical spring gets deformed, that is, it changes in shape or size. This force is referred to as the deforming force. And the ability of an object to regain its original shape when the influence of this deforming force is removed is called elasticity. More examples of such objects include sponge balls and rubber bands. When compressed or stretched, they get deformed, but they soon return to their original shapes. This self-reversing deformity the object goes through when forces applied and removed is called elastic deformation. But is there a limit to the elasticity of an object? Do elastic objects remain elastic forever? Not really. For instance, if a great amount of force is applied to a spring, it simply won't be able to stretch further than a certain point. But if the force becomes excessive, the spring will get permanently deformed and may even break if we keep increasing the force. Hence, the spring does not remain elastic forever. This type of deformation, where the object is unable to attain, or if it only partially attains its original shape once the deforming force is removed, is called plastic deformation. Now let me ask you a question. Suppose we have a rubber string and a string made of steel, both of very tiny thicknesses. Both are identical to each other in terms of size and shape. If we stretch them from both the ends with equal and opposite forces, then which one will stretch the farthest, assuming the deformation is elastic in both the cases? Quite obviously, the rubber string will stretch the farthest. The steel string would barely stretch, but it is important to note that it would indeed stretch no matter how little. It doesn't stretch as far as the rubber string because steel applies more resistance to the deforming force than the rubber does. Moreover, as soon as the force is removed, the steel string regains its original shape and size quicker than the rubber string. It won't allow a deforming force to change its dimension as easily. So, which one would you say is more elastic? Steel or rubber? You would think that the obvious choice has to be rubber, but unfortunately, that's incorrect. There is a general misconception that a lot of us have about elasticity. We think that the more the object gets stretched or compressed, the more elastic it is. But elasticity is not the same as flexibility. In the language of physics, the term elastic has a very different meaning. In physics, we say a body is more elastic if it resists more to the deforming force and reverses back quicker to its original shape after the force is removed. And since steel resists more and reverses back to its original shape quicker, it's more elastic than rubber. We can mathematically define.
So what when we're talking about something that is elastic, it's the ability not like your waistband in your gym shorts that stretch, but it's how much does it come back to its original shape. So there's a couple places who would test these things daily at their shops, and so if we're talking about metrology, places like wire rope, this would be a place where it would really matter. You want to know how much this stuff will stretch, how much it returns to. Another place that you would see that happen here locally is Pro Energy. When they're looking at like turbine buckets, that's what we would look like when you look at like a jet engine. You see the vanes on it, those like that fan shape. Those are called buckets. They stretch really quickly, and then they stay hot for a long time, and they stay in that place. But the idea is when they cool down, they have to return to a certain spot. If they don't, the motor won't spin again. So when they build something like that, they actually build it to wear into itself. So they build this engine with the fact of knowing that these buckets, these fins, will swell out so much so that they will dig into the outside frame of it. And that's actually how it seals it. And so while they're hot, it's digging into it its first time around. It stretches out at that heat range, it stays there. When it cools down, it loses its sealing ability as it stretches back in the right place. But if you grab the wrong material, use the wrong material, and you build a whole bunch of buckets, and then you go build a jet engine, so they're jet engines that they use for electrical creation. And if you do that, then you've got something that can either stall out, that can seal, not seal, or come apart. So knowing the material that you use really matters. The bigger the part, the more it's going to move and stretch. So some of those buckets are like this tall, and they can stretch, 1/8 of an inch. Some of them are really small, and they're only going to move 30, 40 thousandths. But no matter what, it's proportionate to what it needs to be able to move. No matter what we're working on, we've got to factor in some movement in the things that we're doing. So even as you guys are running dies, if you're running thin material, and as that die starts to heat up, the more it strokes, the less clearance that it gets, right? And so imagine if you're running a paper die. So I was just talking to a friend of mine about this the other day. He says, hey, you ever done any kind of paper stuff? I was like, yes, it's terrible. So there's a place that used to be here in Sedalia called Cookbook Manufacturers, and guess what they made? Cookbook. Yeah, they actually didn't make them, they just printed them. And I didn't think there was that big of a market for printing of cookbooks that it would be specifically cookbook manufacturers. So anyways, they also make calendars. And so think about spiral bound, all those little holes on there. So think about a punch and a die clearance on a piece of paper. How much clearance do you think there should be between a punch and a die in paper?
7% of 3,000.
Roughly. I mean, if it's tenths.
We got 7% will.
Yeah.
5 to 10. But,
Yeah.
Depending on how thick the material is, so 22,000 is like 2.5 pounds, something like that.
Yeah. For material thickness.
22,000.
22,000 of material thickness.
Yeah. So if you're talking 3,000, that's pretty tight.
Yeah. So you got 3,000 thickness of a piece of paper. You have a punch and a die, and it's going together. It's punching. Paper is extremely abrasive. Punches like that don't have much die life on them anyways. And so if the temperature in the room changed, the die would get stuck.
You're talking about 1/10.
Like, is enough to change it. And so if you grab the wrong material, so let's say let's say there's 50 spiral little holes on there. And you guys start making punches, but your shift ends and you only get 22 punches made. Austin comes in and he's like, I'm gonna finish up what you got. William, is that it? Very good. Austin and William are gonna finish it up. They're gonna make the rest of them. Well, you guys were making them out of 01, and they didn't know that, and so they just go grab some W1 or some A2, and they start making their punches out of that, and they put it all together, now you got two different metals. And now you got this die that's going, and they're like, half of these punches are hanging up, and these guys are going, well, that's because they didn't make theirs right. These guys are going, well, that's because they didn't make theirs right. Well, somebody's got the wrong material, and now you've got expansion and contraction happening at different times. You got huge problems. Now, lots of times that doesn't happen. I mean, like where I came from, we worked with some pretty thick stuff. You had a lot of freedom, and you could be off a couple thousand. It wasn't gonna matter. But thinner the material that you have, then the more it starts to affect. Just the ability to return back to its original shape is really, really, really important. All right, let's talk about strength, ductility, and toughness.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct, but it's wordy and hard to read. It undermines the writer's message, and the word choice is bland. Grammarly's cutting edge
Flies,
technology
anybody
helps
noticed
you
high
craft
volume of flies?
understandable
You
writing
will-
They cut down a
that
little
makes
bit.
an impact
They
on
should be
your
slowing
readers.
down.
Much better.
We call
Are
them
you
fair
ready to
flies.
give it a try?
So they're the ones that come from the fair. They've noticed now
Visit
there's no
Grammarly.com
carnival
today.
action, and so they're going to the next biggest bunch of clowns, and just come to us. So, gotta work with it. What is this?
In this video, we're going to take a closer look at strength, ductility, and toughness, very important material properties. Let's get started. Strength is a measure of the stress a material can withstand. Two different values are typically used to define the strength of a material, the ultimate strength and the yield strength. Let's define them by taking a look at the stress-strain curve obtained from a tensile test. The ultimate tensile strength of a material is defined as the maximum stress, which is reached during the tensile test, corresponding to this point on the stress-strain curve. It is the maximum stress the material can withstand during a tensile test. The yield strength is defined as the stress at which a material begins to deform plastically.
So have you ever seen something like being pulled apart and like you can see some pressure against it, and then when it goes, it just kind of goes. You're like, whoa, that's where it happened. Like that's what they're talking about. This is where something happened to it. It was pushed or pulled or whatever. You're like, oh, that's where it started to bend. And then here you see the rest of it, the stretch that it gets.
Pressing a material beyond its yield strength will result in permanent deformation after the load is removed. Many structures and components are designed to ensure that they only deform elastically. This makes the yield strength a commonly used criterion for defining failure in engineering design codes. It is possible for failure to occur at stress levels well below the yield strength if the applied load varies with time. This failure mode is called fatigue, and I will.
So fatigue is going to be that long, that consistent amount of lower pressure push against things. You all right? Do you have a seizure?
I almost went on those.
So it's not a million pounds up against it. It's 1,000 pounds consistently. And so here's how I would say it. Most of you guys aren't parents. Mom, 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 mom is just as annoying as mom, right? Like it's just annoying in a different way. Both of those have results that come from them. Both of them end up with a boom, and so different ways of going at it. So you can attack it hard, or you can slowly push up against something. And so a lot of this we're talking about structural. So kind of the fatigue that goes up against something. Set of stairs gets constant bouncing on it, right? So that goes up to my office. There's a set of stairs. They used to not have a brace under them, and when you ran up them, it was like trampoline stairs, and you were like, boom, it was like spacewalk up it. And so finally we put a brace against it because we were like, at some point, even though none of us are like 600 pounds, and I don't even know 600 pounds would do it, like probably 2,000 pounds on it. Even though none of us were at that level, Still, at some point, like, it was just consistent pressure up against that, just on and on and on and on, and we would have eventually had a problem. And we have terrible insurance, so I didn't want it to happen to me.
We'll cover it in a separate video. For some materials, the transition from elastic to plastic deformation is not clearly defined. In these cases, the yield strength can be defined using the 0.2% offset method. This involves drawing a line with the slope equal to Young's modulus and shifting it 0.2% to the right on the stress strain curve. So far, we have only discussed strengths in the tensile direction. But what about the compressive direction? For ductile materials like mild steel, the yield and ultimate strengths are very similar in the tensile and compressive directions. Tensile tests are usually easier to carry out than compression tests, and so compression tests aren't often performed for these materials. For brittle materials like concrete and ceramics, however, the material strength is much larger in compression than in tension. I will talk about why this is the case later on in the video. First, let's look at some examples of strength values for a few different materials. Tensile yield strengths are shown for ductile materials, and ultimate compressive strengths are shown for brittle materials. Graphene is the strongest material to have ever been tested. It is a two-dimensional material made up of a single layer of carbon atoms arranged in a hexagonal lattice and linked by strong covalent bonds. Defect-free graphene has an ultimate tensile strength of up to 130 gigapascals, or 19,000 ksi. I've mentioned material ductility a few times in this video, so now is probably a good time to define it properly. Ductility is a measure of the ability of a material to deform plastically before fracture. Let's return to our stress strain curve. Materials which undergo large amounts of plastic deformation before they break are called ductile materials. These materials fracture at very large strains. Mild steel and gold are examples of very ductile materials. Materials which fracture at very low strains with little to no plastic deformation are said to be brittle.
Okay, so let's talk about what can take a lot of heat, pressure, wear, and just work for a really long time and not have too much problem. Okay. Yeah. How about like an engine block, right? Like it's consistent heat, cold, misuse, constant pressure up against it. But that block is always moving, and then it has the ability to return back to its ductile. Okay, so it's got. So think about your rods on there. They have a constant explosion that consistently comes up against them, and yet they don't break under normal circumstances. They stretch and they compress, and they stretch and they compress, and they just continue to do that over and over again. So they've got ductility inside of them.
Glass and ceramics, like porcelain, are examples of brittle materials. Because they don't deform plastically, the concept of yield strength is irrelevant for brittle materials. There is no defined transition point between ductile and brittle behaviors. Typically, a material which has a strain at fracture of less than 5% is considered to be brittle. Now that we have covered what ductile and brittle materials are, let's return to the question of why brittle materials are much stronger in compression than in tension. There are two factors at play. The first factor is that tensile loads tend to encourage the formation and propagation of cracks, whereas compressive loads do not, as illustrated here. The second factor is that in brittle materials, very little or no plastic deformation occurs to redistribute stresses at existing flaws. This means that large stress concentrations build up at the crack tip, resulting in fracture.
So here's where this becomes like a really big deal. You're a military guy. What was his name? Jeff?
Eason?
Yeah, Eason. So Jeff Eason did, he works with you guys now. He would always talk about, they did a lot of bomb inspection stuff. And And so they were always worried about nicks and dings on stuff because of what could happen, and where it becomes a potential weak break or stress point on there. So like on parts that we might make, parts that you might make for your for customers, or maybe you're the customer, whatever it happens to be. Even a part that gets completely done in a machine and then gets dropped and gets a ding on it could now be a potential failure point for that part. Lots of times it doesn't matter. I mean, if you're punching out 1/8-inch thick quarters, all day long, probably not a big deal. But if you're doing something that has real finesse to it, or holds insane amounts of pressure, a boiler, style behind it, those little dents, those dings inside of those surface imperfections, even undeburred edges can create fracture points or opportunities to fail on a piece of material. So most of the time for us, a good deburred edge is just something that's not sharp. But it can also have something to do with the performance of how this piece functions. I mean, I've made pieces anywhere from things that went on the space station to tractor tire washers, and so you just kind of figure out the value of what it is that you're doing. Is it worth spending the time on it? Is it not worth spending the time on it?
In ductile materials, plastic deformation occurs, which relieves these localized stresses. Ductility can be dependent on temperature. A lot of different types of steel, for example, are ductile at room temperature, but become brittle when the temperature drops to below the ductile to brittle transition temperature. This transition temperature is an important design consideration, because ductile failure is normally preferred to brittle failure. One very famous example of brittle failure is the Titanic. The icy waters of the North Atlantic are thought to have caused the steel of the ship's hull to drop below its ductile to brittle transition temperature, resulting in catastrophic brittle fracture. Toughness is the ability of a material to absorb energy up to fracture. It can be calculated as the area under the stress.
Okay. I'm going to flip the lights back on. He talked about the Titanic, and I want to take just a second and go the other direction of that. And so I'll go out of that for a second. So has anybody ever heard of the Hyatt Regency building failure happened in Kansas City? It was up till right before 9/11. It was even after 9/11. It was the largest structural building failure in the United States for 50 years. And so the Hyatt Regency in Kansas City it was a couple level building, and it's still there today. The whole thing was plagued. There are tons of YouTube videos out there if you want to see this, if you're totally bored and can't sleep. And so when they built this thing, they said, we want to have these really long kind of bridges expand from side to side of the building. And so then they built it, and they tried to build a lot of stuff with glass, couldn't do it structurally, so they had to change some things. And so anyways, they built these, so rooms and offices are over here, and rooms and offices are over here. And then they have these bridges that kind of run out, and they're on suspended by these rods that go all the way throughout the building. And so picture 3 suspension bridges on top of each other, all about maybe 10 to 15 feet, probably 15 feet apart from each other. And so what they did was they had this dance contest there, and so hundreds of people, and so they're all out dancing. It's kind of like one of those things, like you get tapped out, you're like, hey, you guys suck, get off the dance floor kind of thing. And so it continued on throughout the day, the evening, the night, whatever it might happen to be. Can't remember all the details on it. But what happened was one of the upper levels collapsed, and then it fell down onto the lower levels, and then it pulled the whole thing And so then they brought guys in from all around the world to try and figure out what was going on. This is literally an hour and a half away from here. And so they brought in like seismologists, you know, and trying to figure out, was it the vibration that went on? What was going on that caused this thing to fracture? What caused this upper level to break and to fall down on this other levels? And so just to kind of emphasize how things go and the order of importance is, so ultimately what happened was these suspension bridges were kind of roughly like this. Rod goes down through it all the way down, okay? So what happened was, when they built it, the specs for building it was these are C-channel. So they were supposed to be like this. Okay, then the rod goes through it. This is exposed. But what happened was architects came in and they said, hey, that's not going to work because we can't do anything with this. We can't wrap it. And so they flipped it. So the rod goes through it like this so that this is the backside exposed. So why does that matter?
No, there's room to vibrate internally versus being snug up against the solid stone.
It absolutely has that to happen against it.
And now it's also flexing.
Absolutely.
Towards the center.
Absolutely. So it's made so that it can move, right? I mean, the C-channel knows that, you know that it has some flexibility built into it. At some point, this gets to a point where it buckles, and once one goes, all of them go, because they support each other, right? So whoom, all the way down, and so they figure out which joint is the one that broke that caused all of the other ones to break, and it changed the way that they did structural stuff for generations. So this happened in about, I bet this happened in the 70s, and so it wasn't really that long ago. I think I was alive when it happened, but I didn't know about it until I came here, and we were doing some research on trying to find some practical applications for this, and we were talking one day, and we come across this. Alan Strange was like, I remember when that happened. I was like, you're old. And so I was like, I don't. And so I started looking it up, and I was like, this is a perfect example of something that would be easy to do. Flip this around, yeah, it makes sense. Now we can attach something to that. We can wrap that beam, make it look nice and pretty. Here's where it has strength. Here's where it doesn't. Easy mistake to have happen. They walked through all these change orders, and they never could actually figure out who made the decision to flip it. You know that guy wasn't ever going to give himself up. You know, he was like, I don't know, I'll stick that thing. Go. And so anything you could do to get out of there, you know. And so anyways, they figured out how it happened, what happened to it, and it changed the way that a lot of things go. So it's just kind of that culmination of all these things coming together that brought this whole thing down. Really just by a simple procedure here. And so like, I just want you guys to be thinking about that as you're building things, as you're putting things together. If you find yourself in a spot where you're building assemblies, how you put that thing together, where it goes, you know, what goes where, what gussets go here, what gussets go there. You weld it, you heat it, you do these things to it. Did I affect it? So if I'm building gussets for this framework that I'm building, I can't find anything except for 4140 to use, and I make all my gussets out of 4140, I just screwed myself and everybody else who's going to walk on this thing. Because 4140, as soon as it gets hot, it heat treats, and now it becomes ultra brittle, and it's going to cause a crack. And so I need to know that before I get started on these things. And that's why, because I know, like, you can look at these things and think, this is not very important to my life. This is very important to your life. This really, really is. Because you're going to be in the shop at some point making some decision. Am I going to use a cold rolled steel? Am I going to use the 4140? Which one is the right one to use for the right thing? You need to know those things. Sometimes there's somebody there to go behind you or in front of you and go, whoa, whoa, hey, don't use that or use this. Other times you are going to be in a spot. You make more decisions that are out of your ballpark when you're second, third shift, don't you? Because nobody's around. And like, if you're going to get the job done, you've got to make a decision. I'm going to use this wrong material. I'm going to change this thing so that we can run tomorrow, or I'm going to stop. I need to be able to make sure that I'm bringing informed decisions onto the table. So those things really, really do matter.
What was the name of that building?
It's the Hyatt Regency. Hyatt, can. 1981. Yeah, I was alive, barely. I was young. I know you wouldn't think I was alive, but I was.
My dad would have been 6.
I would have been 6. Yeah. Yep, absolutely. It's pretty amazing stuff, though. It really is. Okay. Last one I think that we're going to be able to do today. Promise it'll be equally as boring as the others.
And for tough mothers, Grainger offers supply.
To understand the benefits of heat treating processes, first requires an awareness of metal and alloy structures. When a molten metal solidifies, the atoms arrange themselves into definite patterns called crystal structures. The two most common crystal structures in metals are body-centered cubic and face-centered cubic. These crystal structures grow uniformly in all directions within each developing crystal.
So this is
As the metal
structural
cools,
of
these
your
crystals
materials
are
that you're working
confined
with.
by the adjacent developing crystals, forming grains. The line of intersection between grains is called a grain boundary. Because the grains form independently, their crystal structures develop tilted in various directions. All atoms in these crystalline structures are held in place by electromagnetic attraction to neighboring atoms. If a force or load is applied to a metal, these electromagnetic bonds stretch, allowing the atoms to move slightly. When the load is removed, the bonds pull the atoms back into position. If the applied force exceeds the metal's yield strength, those electromagnetic bonds will break, causing permanent stretching or deformation. To make metals stronger and more resistant to deformation, it's necessary to strengthen their crystal structures. This is done by adding alloying elements, which are other metals or non-metallic elements like carbide. The addition of an alloy introduces foreign atoms within the crystal structure of the base metal, disrupting the structural uniformity. This disruption results in increased strength.
That got loud. Okay, so I'm going to go back just a smidge into that video.
All atoms in
And
these crystals.
so here's what I want you to, you can go turn the light back on, if you don't mind. Here's how I would try and define what's happening during the heat treatment process. And so you guys are going to be doing this, you need to go tell me what is going on while these things are happening, because it matters. What I don't want you to do is become the people who are like, oh, this is how you heat treat it, step 1, step 2, step 3, and not know what's going on inside of that. Huge differences between those kind of things. So let's just assume that this is our base metal, 1018, whatever I happen to be. And we want to make it into something else. And so like the video showed, you start to add those alloys inside of there. Now, when you get to a point that you want to start to heat treat it, You've got to give it, yesterday I told you 1333 was that upper transformation temperature, upper transformation table, so there's kind of a line you're on the sand there that makes it, it's just hot or it's heat treated. What happens is one of those alloys in there is oftentimes carbon. When carbon is added into it, probably just the simplest way that I could probably describe it is when you take a piece of material and you're going to heat treat it. So let's just say we take a piece of O1 here and we get this thing hot. This has carbon in it, okay? I know because you can taste it. That's not true. But it's got carbon in it. Now, when I heat this thing up to say probably O1 around 1475 is probably what it needs to hold at for a while. I'm going to heat it up to 1,000. I'm going to crank it. I'm going to step it up to 1475 in a kind of a prescription or a recipe. The carbon inside of it, by that time, is going to essentially, this isn't exactly how it happens, but this is just my simplest way of saying it. It's going to liquefy and attach itself to around all of those other atoms. While it's doing that, if you can catch it in the right state, in the right phase, then you pull it out of the oven and you immediately cool it down, either by O1 goes to an oil quench, so you put it into a quench oil. A2 would go to an air quench, so you're going to rapidly cool it down. W1, water quench on there. D2, oil quench, several different ones that you can do. Some of them you can mix and match. So what you're trying to do is you're kind of trying to trap that in that liquid state or in that phase change, and you're like, I got it, snap it down into the water or whatever it might have to be, you lock it down into that spot. Now, if you are too slow at doing that, it will begin to lose Rockwell points. Rockwell points are what we're looking for. That's our goal in that. So we're trying to bring it from Rockwell 8, super soft, easy to file, to Rockwell maybe 58. Now it's in that die life area, so it's got some strength to it. It can handle a hit for a while. Maybe we're trying to get into the 50s where it's strong and tough. We take it and check it on our Rockwell testers. Several different ways that we can identify what that is. So when you bring something out of the oven, so I don't know that we'll be in it next week, but we'll be in it probably by the next week after that we'll heat treat some samples. Your speed that you move out of the oven into the quench oil, however fast you do that, needs to be done twice that fast, okay? So typically people will open up the oven and they're like, what? Check that out, what was that? And then they go and take it out and they're like TikTok, and they get lost and distracted and then go into the oil. If you don't go immediately from oven to oil within like that, you will start to lose value, okay? Not in life, I think you guys are all valuable, but you're gonna start to lose Rockwell point value, okay? Typically, it's going to go into the quench, it's gonna be cooled down, you're gonna Rockwell it, it's gonna be too hard then, it's gonna be over Rockwell, you're gonna draw it back or temper it. When you're tempering it, you're gonna bring it back up to another temperature. You're going to then bring it back, and what you're gonna do is you're kind of soften the edges on that, okay? So right after the point that it gets quenched, it's like a Jolly Rancher, right? Like you bite into it, and not like a Jolly Rancher has been in your pocket, like a Jolly Rancher out of that freezer, yeah. That's like you bite it, and it's just like, all it like shards in your mouth, you know? Like who would eat a Jolly Rancher anyways, man? There's Kit Kat and Snickers. Who likes a Jolly Rancher?
Only blue ones. Blue ones are the best.
Yeah,
Blue ones.
blue or cherry.
Blue or cherry. Okay.
I'm grape.
Blue. I'm not grape anything. You probably failed. So,
I was just kidding.
yeah. Yeah, I hate Jolly Ranchers, and I only like what you like. Yeah. So it's like that, and so what you're trying to do is so tempering is kind of like taking that really cold Jolly Rancher and put it in your pocket for a little bit, where like you start to bite into it, where you can push it to crack, but you could just get stuck in your teeth, right? So it's like finding that happy medium between those two. So everything is like that. So the head of a hammer, it's a certain hardness value so that it doesn't shatter and that it doesn't get all swollen and destroyed on it. A die, it's manufactured to a certain hardness so that it stays hard, it stays in the shape, it lasts for a certain time. things that are soft are oftentimes heat treated or annealed down to a place where they are at a certain softness value. So think about a bullet. A bullet that is ultra hard coming out of a gun does not make sense, does it? Like the anticipation is that when it hits when it hits its desired target, which is not a person, ever, okay, it does something, right? It mushrooms out, it explodes, it's designed to do those things. It has a desired hardness, toughness built into it, so it does something at a specific time. So everything has this technology. A washer that you tighten down on a bolt has a certain amount of stretch, push, compression that goes onto it. Torque to yield head bolts, right? Like when you tighten them down, they stretch a certain amount. They don't go back after they're done, okay? No matter how badly you want them to. And so there's just several different ways of doing those things. Okay, we are going to, we'll stop, and, because clearly somebody wants me at the door.
Is there any immersive this week?
No, there will only be, yeah, the only be
Structures are held in place by electromagnetic.
the wrong video, stop it.